So today we continue learning about double integrals, and we turn to a very specific question. We won't get all the way to an answer today, but the question is, what if the domain of integration is not a rectangle? Last lesson was purely about rectangles, but suppose, for instance, that we have a population function. That is the population density, people per square kilometer, as a function of space, and we want to perform an integral of that function over the domain consisting of the United States. That integral will give us the total population of the United States. However, this domain, D, over which we want to integrate, is not a rectangle. So we can't just do a simple integral a to b, c to d. In general, this problem is not easy. Domains with very complicated shapes like this can be mapped to simpler domains, and that can be shown in a much later class. But here we will investigate some somewhat more difficult domains as a way of building toward more complicated domains. So we'll start with some purely conceptual statements before doing some examples. Our book introduces two types of integral domains, which are very similar to each other, with one important distinction that we'll see. So it classifies as type 1 domains, domains where the boundaries on X are straight lines. So we have here a straight line, and here we have a straight line. The first at the point X equals A, and the second at the point X equals B. But the boundaries on Y are functions of X. So we have a lower boundary G of X and an upper boundary H of X. We can write this in domain notation by saying that X lives on the interval A to B, but that Y lives on an interval that depends on X. So depending on the value of X, Y has a different domain, and that gives us this shape. So because the domain of X and Y can be written in this relatively simple domain notation, we can represent the integral of some function f of X and Y over this domain in a relatively simple way using our existing integral notation. So we have here our integral of f. With respect to y, the bounds depend on x, and with respect to x, the bounds are just constants. So this works out fine. The only caveat is that because the bounds on y depend on x, that integral needs to be inside the integral on x in order to get a constant at the end. So when we do this inner integral, the integral of f of x and y with respect to y with bounds that depend on x, this will integrate out the y because it's a definite integral. So the y will disappear and we'll be left with just some function of x on the inside. So then when we integrate that function of x between constant bounds, a to b, we'll get a constant, which is what we expect when we integrate a function over a domain. So very similar story for the other type of integral that our book defines. It calls them type 2 domains. Here it's just a 90-degree rotation of the previous case. It's where the y boundaries are straight lines corresponding to y equals c and y equals d. But the boundaries on x are now functions of y. So y lives on the domain c comma d, but the domain of x depends on y. So we can, again, this can be representable as a double integral, where we integrate first with respect to x, and the domain, the bounds on x depend on y. Again, however, as we do this integral, we will be left with a function of y, and so that needs to go inside the y integral so that when we integrate the result from c to d, we get a constant. In both cases, if you do it in the wrong order, you get a meaningless result. If we did this in the wrong order, we would first eliminate the y, and then we would do an integral on x, which would leave us in terms of functions of y because of the boundaries depending on y, and so we would have I dependent on y, and that doesn't make any sense. So we have to do these in the right order when one of the domains in one of the variables depends on the other variable. So I hope conceptually this makes sense. Let's now do some examples, a couple anyway. Two notes: you often have to sketch the domain to figure out which type of integral is more appropriate, whether you should do x first or y first. And some problems can be done either way. So here we'll do our first example. We integrate the function x squared plus y over the domain D, an area integral, a double integral over the domain D, which consists of the region between the functions y equals x and y equals x squared. So we sketch these functions, y equals x and y equals x squared, and we see that they enclose a region here in between them. And we now ask, should this be a type 1 or type 2 integral? Should I first do x or should I first do y? Another way to think of this is to say, is this easier to slice the domain into x slices or y slices? And that's kind of indicative as what I've drawn here. This is easier to slice in the y direction, whereas a type 1 is easier to slice the domain into pieces in the x direction. So here with this example, we have a situation where we can slice either in x or in y. So let's go ahead and set up both integrals. We'll do them both, and we'll see in the end that we get the same answer as we should. So suppose we're going to do, I have said this incorrectly, y first, with y domains being functions of x. So then we would say x goes from 0 to 1. Y, on the other hand, goes from the lower function, which is x squared, to the upper function, which is x. So we get an integral where we first do y. Y goes from x squared to x, followed by an integral with x going from 0 to 1. So this first integral, in y, the x squared is treated as a constant. We integrate a constant, we get the variable, so we get x squared y. We integrate the y, we get 1/2 x squared. All of this must be evaluated at x and at x squared. So we plug in those values. We get here x squared times x plus 1/2 x squared. That's this piece. And then we have to subtract x squared times x squared, and then subtract 1/2 x squared squared. So that's minus x to the fourth minus 1/2 x to the fourth, right here, at the lower boundary. This is then 3/2 x to the fourth. We now integrate x cubed because 1/4 x fourth, 1/2 x squared becomes 1/6 x cubed, and 3/2, negative 3/2 x to the fourth becomes negative 3/10 x to the fifth, evaluated on the x boundaries 0 to 1. At 0, they're all 0, so we just plug in 1. We get a fourth plus a 6 minus 3/10, and when you work out the fractions, that's 7/60. However, we could just as well have sliced this horizontally and let y go from 0 to 1, in which case x, the boundaries on x now depend on y. So again, this would have been x first, and then y. The x boundaries, the lower bound on x is going to be this line x equals y, and the upper bound on x, again, x is increasing in this direction, the upper bound on x would be solve for x, x equals the square root of y, or y to the 1/2. So we would do an x integral first, where x goes from y to y to the 1/2, followed by a y integral from 0 to 1. That would be integrating in x now, 1/3 x cubed. Y is a constant. Integral would be xy. We then plug in y to the 1/2 power, giving us 1/3 y to the 3/2 plus y times y to the 1/2, which is another y to the 3/2. And then subtract the value at x equals y. That's minus 1/3 y cubed minus y squared. So top boundary, bottom boundary. Now it's just a matter of integrating. This here becomes 1/3 plus 4/3, 1 plus 1/3, which is 4/3 y to the 3/2. 4/3, when we integrate that, we get x to the, that should be y to the 5/2 divided by 5/2, or 2/5, minus 1/3 times 1/4 y to the 4th, and minus 1/3 y cubed, evaluated at 0 and 1. Again, at y equals 0, we get 0 here, and so we just plug in y equals 1, giving us 8/15 minus a 12th minus a third, which is again 7/60. They should be equal because we just set up the integral in two different ways. I'll note that not every problem can be done both ways. This was just an example, both showing us how to set up these integrals and pointing out the fact that sometimes you can do it two ways, but many problems can only be done one way. Now, a last sort of note. Sometimes we are faced with integrating over a domain that is too complicated for a simple integral that's set up like we did before. However, you can always split any domain into multiple pieces as you find convenient so that you can then parameterize each piece in a simple way. So here we have sort of a jungle hat, which could be parameterized. This piece here is a circle, which is easy to slice vertically in the x direction. So this could be a type 1 region. Here we have straight lines at the top and bottom and slanted lines on the sides. So this could be a type 2 region that we could slice in this way. On Valentine's Day, we could integrate over a heart. These could be type 1 regions like this, and this could be a type 2 region like this, and so on. Or on St. Patrick's Day, we could do a 4-leaf clover, type 1, type 2, and the inside is a rectangle, which can be done in either order. So we can break more complicated regions down into simpler regions and do each region in its own most appropriate way. So we'll do one example of this, which is a little bit complicated for these videos, but should be okay. So we have the integral over a domain of the function xy, where the domain is bounded in the third quadrant by the unit circle, in the second quadrant by this function here, and in the fourth quadrant by this function here. So here's our boundary in the third quadrant, the unit circle. In the second quadrant, this is a parabola with intercepts. It's a parabola pointing down, negative x squared minus x. And it has intercepts at 0 and negative 1. That's this right here. And in the fourth quadrant, this is a parabola opening to the left, negative y squared minus y. It has y-intercepts of 0 and negative 1. And that's this piece right here. So, having sketched these pieces suggests to us a way in which we could break this down. So this region here in quadrant 2 looks like it'll be easiest to do y first, followed by x. X is the simpler, and so we do the more complicated y first. That's a type 1. This region here in quadrant 4, that'll be a type 2. And this region here in quadrant 3, we could do it either way. Let's go ahead and just do it as a type 1. So we set up our integrals. We have, this is quadrant 3. This boundary set as a function of y is 1 minus x squared, which is the lower bound. Negative 1 minus x squared, and the upper bound is 0. So here's our lower bound on y, our upper bound on y, our lower bound on x, our upper bound on x. We do y first, and then x. Here's the integral in quadrant 2. Lower bound y equals 0, upper bound y equals negative x times x plus 1. Then for x, boundaries are negative 1 to 0. Finally, in quadrant 4, we do lower bound on x, 0, upper bound on x, negative y times y plus 1. And bounds on y, negative 1 to 0. So let's proceed. We now integrate this second integral, this first integral, first with respect to y, giving us 1/2 y squared times x. That must be evaluated at 0 and negative square root 1 minus x squared. Over here in our second integral, we integrate first with respect to y. Again, 1/2 y squared times x, where the bounds are now 0 to negative x, x plus 1. And finally, integrate once with respect to x. We get 1/2 x squared from 0 to negative y, y plus 1. We can proceed with each of these in greater steps. We have here, pull the 1/2 out, substitute here 1 minus x squared in for y, and that will square it, giving us 1 minus x squared. That's evaluated at 0. We get 0, and then subtracting the value when we plug in this gives us negative x times 1 minus x squared dx. Then these two integrals here we see are actually the same. This is going to be 1/2 y squared evaluated at negative x plus 1. Plug that in, and we're going to get 1/2 x times x squared times x plus 1 squared from negative 1 to 0. Here we'll have y times y squared, y plus 1 squared, pull out the half, again from negative 1 to 0, integrated against y. But these are the same integral with x and y just switched. So because of that, we can combine them into a single integral. So it's twice, pull out the 1/2, negative 1 to 0, x times x plus 1 quantity squared dx. Simplify, expand out these polynomials. This becomes x cubed minus x. This one, x to the 5th plus 2x to the 4th plus x cubed. Integrate 1/4 x to the 4th minus 1/2 x squared. This one, 1/6 x to the 6th plus 2/5 x to the 5th, 1/4 x to the 4th, and so on. They all are 0 when x equals 0. We plug in the negative 1, and we get fractions, which when we simplify, we get a number. So the number itself, not so important, but the idea of breaking down a more complicated domain into simpler pieces, each of which can be treated as one of these ways to type 1 or type 2 domains. I want to emphasize here that we have not magically changed this integral here into an integral over x. We're not like magically shifting the domain around, but when we get to the point where we see that these are the same integrals, this integrated against x and this integrated against y, we simply say, okay, there's the same integral with different dummy variables, which means we're going to get the same number. So I'll change this dummy variable y here to an x. It's not that we are moving the domain or pretending it's oriented in the x direction or something. At that point, we're simply changing the dummy variable on the inside of the integral. So that's a mathematical step rather than a geometrical step. All the geometry is basically done here in the very first line where we set these integrals to correspond to these domains. Anything we do after that is just mathematical manipulation.